Great. This is section 4 of chapter 11, and this is the last section in this chapter and the last section in this class. So in this section, we are looking at sequences and series still, but now what we're going to do is find their sums. So adding up all the terms of a sequence or series. So we'll see this symbol a lot, and you'll see this again in Calc 1 and Calc 2, and this is called a summation symbol. So at the bottom of it, you'll have the lower limit or the index of summation, and then at the top, you'll have the upper limit or the last term of the sequence or series that you're adding up. And then right here, you'll have the equation or the explicit formula of the term or of the sequence. So what this means then is that we are adding up all of the terms. So if this said, for example, from 1 to 10, we'd be adding the first term plus the second term plus the third term all the way to the 10th term. So for this first example here, when we see this summation symbol from 1 to 5, what this is asking us is to plug in 1, plug in 2, plug in 3, plug in 4, plug in 5, and then we're going to add all of those up. So we have the summation from 1 to 5, and plugging in 1, 1 cubed is 1. Plugging in 2, 2 cubed is 8. Plugging in 3, 3 cubed is 27. Plugging in 4, 4 cubed is 64. Plugging in 5, 5 cubed is 125. And all of those added up gives us 225. And so that's how we would do these types of problems. So the next two examples ask us to write this in summation notation. So we can see that what's changing from one term to the next term to the next term is this number right here. So 1 and then 2 and then 3, and they're all being raised to the fourth power all the way to 12. So we can see that we're starting with 1 and we're ending at 12. And the formula that they're all being plugged into is I to the fourth power. So that's how we would write this in summation notation. The next one, we can see a few things changing. So not only is the number on top changing, so it's going from 1 to 2 to 3 all the way on, but also the bottom number is being raised to different powers, to the first power, to the second power, to the third power. And so we can see that both things there have an n, and because this is going to the nth power, we can actually see the formula right there. So writing this in summation notation is going from 1 to n, and the formula is n, or rather I. Sometimes we use K, sometimes we use N, sometimes we use I. We'll just stay consistent and say from I over I to the nth power. Okay. All right, now for arithmetic and geometric sequences, the arithmetic sum, if you have a bunch of terms that are in arithmetic sequence and you want to add up, the first 30 terms or the first 50 terms, this is the formula you're going to use, and you're going to need to know this formula. So the first example here says add up the first 100 terms of the sequence, 1, 3, 5, 7, 9. Well, we can see that our common difference here is 2. And so we know our first term is 1, but we need to know the nth term. So in order to find the 100th term, we're going to use the formula for finding those that we learned back in section 2. So a sub 1 plus d times n minus 1. So if I want to find the 100th term, that would be the first term, which is 1, plus my common difference, which is 2, times 100 minus 1. Well, my common difference, I should have written 2, not d here. 2 times 99 plus 1 gives us 199. So my first term is 1. My last term is 99. The only other thing I need is how many terms, and we're told we're adding up those first 100 terms. So S sub 100, notice it's not A sub 100, now it's S for sum, sub 100 is equal to 100 over 2 times the first term plus the last term. And when we multiply all of that out, 200 times 50 gives us 10,000. All right. So the next example, given to us in summation notation. And so we can see we're going from 1 to 25. So we're adding up the first 25 terms, but I need a 1 and I need a 25. So I have the formula right here. I can plug in 1 and plug in 25. If I plug in 1, 1 times 5 is 5, minus 9 is negative 4. 25 times 5 is 125, minus 9 is 116. And then we have 25 terms. So S sub 25 is equal to 25 over 2 times negative 4 plus 116. And when we multiply all of that out, we get 1400. So if we took the time to add up 100 terms there, it would add up to 1400. All right, so the next one says the sum of the first n terms of a geometric sequence. And you can see here that this is the formula that we're going to use. You're going to need to know that. And so if we're adding up however many terms from a geometric sequence, this is the formula we're going to use. So this first example here says find the sum of the first 8 terms of the geometric sequence. And we start at 81 to 27 to 9 and so on. So the first thing that I need to find is my R value. And if you recall from section 3, R is the second term over the first term. So 27 over 81, which reduces to 1/3. So that's my R value. Now I need to find the sum of the first 8 terms. And so my A1 is 81 times 1 minus my common ratio 1/3 to the nth power, which is 8, over, and then we have 1 minus R. Okay. So a couple things we can simplify there. 81 times 1 minus, and 1 to the 8th power is 1, and 3 to the 8th power, I'm going to leave as 3 to the 8th power for now. All over 1 minus 1/3 is 2/3. If you're not sure how I got 2/3, 1 minus 1/3 is the same thing as 3 over 3 minus 1/3, and that gives us 2/3. So this is my kind of scratch work off to the side here. All right, so continuing on, I can go ahead and instead of dividing by 2/3, I can flip that bottom fraction so it becomes 3/2. So I have 81 and then times 2, not 2/3, 3/2. 3 over 2 times, and then the inside of my parentheses here, instead of 1, I'm going to write 3 to the 8th power over 3 to the 8th power minus 1 over 3 to the 8th power, so that I have a common denominator. And then 81 times 3 over 2, let's see, 81, actually 81 times 3, I don't want to write that as a higher number. 81 is 3 to the 4th power. Let me just write that really quickly here off to the side. 81 is 3 to the 4th power. So 3 to the 4th power times 3, that's going to become 3 to the 5th power over 2 times, and then I can write this as a single fraction now. That's 3 to the 8th power on bottom and 3 to the 8th power minus 1 on top. So I see here that I have a common factor between the top and bottom that can reduce. So I have 3 to the 5th and 3 to the 8th. 5 of those can cancel, and I'm left with 3 of them on bottom. So if you type these numbers into the calculator, they're going to get really big really quickly. But what we're left with now is 3 to the 8th power minus 1 on top. And then on bottom, we have 2 times 3 cubed. 3 cubed is 27, times 2 is 54. So my reduced fraction, or my simplified fraction here would be 65/60 over 54. Those are both even, so if we divide by 2 on top and bottom, we end up with 3280 over 27. And that is my answer. And I want that exact answer as a fraction, not a simplified answer using, or not a decimal answer that's rounded. All right, so the next one is written in summation notation, and they're asking us to find the sum. The base of your exponent is your R value. So R equals 2. And I can find my first term, a1, by plugging in a 1. Well, 2 to the first power is 2 times 6 is 12. So if I want to find the sum of the first 10 terms, I have my first term, 12, times 1 minus R, which is 2, to the nth power, and n is 10. And this is all over 1 minus my R value, which is 2. So simplifying this, I have 12, and then 1 minus 2 is negative 1. So I can write negative 12 times 1 minus 2 to the 10th power. And that's really just ready for the calculator. There's not as much simplifying as in the previous example. So this gives us 12,276 as my sum. Now, one of the interesting things about infinite geometric series is that we can actually find the sum of infinitely many terms. So if you were able to spend all of eternity adding up numbers, we could add up infinitely many numbers, and that's what this would give us. The only infinite or a geometric series that we can do this for is if our R value is between -1 and 1. So if your R value is bigger than 1 or less than -1, we cannot find the sum. But if it is between -1 and 1, then there is a sum that we can find. This is a concept you'll revisit in Calc 2. So in this first example here, it says find the sum of the infinite geometric series, and it's -3, 1, -1/3, 1/9. So I need to find my R value, and that would be 1 over -3 or -1/3. Well, that is between -1 and 1, so I can find this sum. And it's not S sub n because there's infinitely many terms we're adding up. Now my A1 is -3, and then 1 minus my R value, -1/3. That becomes -3 over 3 over 3 plus 1/3. So -3 over 4/3. And then when we divide fractions, we flip the bottom and change it to multiplication. So -3 over 1 times 3 over 4. And that gives us our negative on this one. And that gives us -9 over 4. All right, for our last problem here, it says express 0.9 with a bar over it as a fraction in lowest terms. Now this 9 with a bar over it means 0.9999999. So if I have 0.99999 going on forever, I can rewrite that as 0.9 plus 0.09 plus 0.009 plus, and I can keep going. Okay, so if I were to rewrite this like that and then try to find this sum, my R value would be 0.09 over 0.9. Well, 0.09 is the same thing as 9 over 100, and 0.9 is the same thing as 9 over 10. 9 over 100 times 10 over 9, those reduce, and we're left with 1/10. Okay, so then finding the sum, since that is between -1 and 1, would be my first term, which would be 9/10 or 0.9. And then my common ratio is 1/10, so 1 minus 1/10. And 9 over 10 over 1 minus 1/10 is 9 over 10. And anything over itself is equal to 1. So if we could add these up onto infinity forever and ever and ever, it would be equal to 1. And that is the last question in this section and in this chapter.